Hello and welcome back, everyone. This is the third week of lithium-ion battery pack design considerations, and in this week we will be mostly concentrating on the most important part, which is the BMS considerations. So, in the last couple of weeks, you might have heard about BMS slightly, where we say that the wiring voltage sensors goes to the BMS, and BMS is something where we can program it, etc. So now is such the place where we will be concentrating more on BMS, and we'll understand what are the capabilities of BMS, what are its different architectures, and how does BMS save the battery pack from effect of abusive C rates. What are the main functionalities of BMS? So this is what we would be covering in this week. Start off, we'll have a quick recap on what we did in the previous week. We had a few topics which are related to the types of welding process, what are the busbar materials used, how the welding process is done, what are the different process changes with respect to different form factors of the cells, how is the heat generated in a bus bar, and how is the heat generated in a cell. We also have looked into thermal loop designs for cylindrical cell, pouch cell, prismatic cell. What are the different thermal calculations that is to be done to understand the temperature rise due to the heat generation, which is a combination of internal resistance, SOC, etc. And we also had a session on ingress protection levels, what are the different sealing types and how the gaskets are designed, and what are the different gasket materials used for the battery. So this is a recap of what we did in the week 2, and now what we'll have in the week 3 is this. We would cover the topics related to BMS, what are these terminologies, what are the voltage cutoffs through BMS, what is its effect on the capacity, and what are the different C rates, BMS protection features like C rate protection features, temperature protection features, and we'll also discuss on what is SCI layer. This is something which you might have read somewhere, but we would discuss on this SCI layer, which is the cause of capacity degradation or the failure of a cell, and what is its effect on that. What are the different types of BMSs, and how are they classified into high voltage and low voltage applications, and then we'll also check on what are the low voltage pack architectures along with high voltage architectures. Also we would discuss what are the low voltage architectures, what are its functionalities mainly for high voltage and low voltage, what are the main differences between them, and then we'll touch base again on the cooling plate attributes, how are they integrated, and what are the driving factors for the cooling plate, and then we'll also see what are the abusive usage conditions, its effect on the cell, and how does BMS overall at the end you will have understanding how will BMS protect all those abusive usage conditions on the cell. So these are the table of contents, and let us focus on what are the learning objectives. As we saw in the table of contents last week, like our focus week 2 was mostly on the cell and its characteristics and selection of right cell, how the modules are made in the last 2 weeks, or what are different types of chemistries, form factors, etc. But this session would mainly concentrate on the BMS, which is the heart or brain of the battery pack, which is also mentioned as battery management system. Battery management system, how does it functions? And we'll have understanding on what are the different types of BMS used, what are its objectives, how battery behaves when subjected to different abusive conditions, and how would BMS control it in preventing thermal runaway or failure of the battery pack, etc. So we would also get some idea of understanding the selection of the right BMS for this application, how is the BMS mounted, which area is mounted for the BMS, how does the cell deteriorate due to abusive user behavior, and how does the BMS help in controlling it. So these are some of the objectives of this session which we will go through. So before we go directly into the BMS, we'll understand what is the BMS, voltage terminologies associated with it, so that this would be helpful for you to have a clear and easy understanding in the next coming slides when we talk about BMS. So firstly, what is state of charge? So SOC, we have heard about this in the last 2 weeks number of times. We have heard about DOD number of times. But what does that mean, SOC? We know state of charge, that's the abbreviation of it. But what does SOC mean? So SOC is nothing but the amount of charge that is available in a cell. It is similar to a fuel indicator. Now SOC indicators are also available for the battery pack. You can have a battery pack and you can have a SOC indicator, and that will show the amount of charge that is there in the battery pack. It is similar to a fuel gauge that you have in a normal IC engine. When the fuel is 100%, the tank is full and your indicator shows lowest point, that means your fuel is empty. It is the same over here. SOC indication starts from 0 to 100, where 0 is empty, 100% is full, and this is applicable for charging. That means the amount of charge is left in the battery is what indicated as state of charge. But whereas depth of discharge is the reverse of SOC, which means that is mainly during discharging. So this is a little bit tricky to understand. Like now see, now SOC is the amount of charge. If we have consumed 20% of the energy, which means the SOC is 80% left and 20% is a consumption. But when you say depth of discharge, that means that 20% becomes your depth of discharge. I understand. Like the amount of energy that has been consumed is your depth of discharge. That's the reason we say that is inverse of SOC. So when you say your depth of discharge is 100%, that means you have consumed the whole of the power. You have consumed everything what is there in that. So that is how you say as depth of discharge. So it is the opposite of what SOC is. The amount of energy that has been consumed is called depth of discharge because it has been consumed. So now in this slide, when we talk about depth of discharge in SOC, this will give you a much more clear picture. Also we have cutoff voltages. So maximum voltage of a cell is actually the cell which is actually the voltage that is reached during charging. And we have minimum voltage, that is the voltage which the cell has reached after being discharged. So that are the cutoff voltages which we have already understood. Like we have three different voltages: nominal, maximum and minimum. It's the same. Now when we say about SOC, DOD and etc., here is what we need to understand. Now consider this as a cell. The first one being fully charged, SOC up to 100%. The next one, the least one, is SOC 0%. So SOC is 100, the inverse is DOD, 0%. And SOC is 0, the inverse is DOD, 100%. So when this amount of energy, this white area is the amount of energy which has been utilized, that becomes the depth of discharge. So this is the amount of depth the discharge has gone up, and the remaining becomes the state of charge. So this amount of charge is still available in the battery, whereas this amount of discharge has taken place. So that becomes the depth of discharge. So usable capacity is nothing but depth of discharge into normal capacity. Now you would understand the equation of what is depth of discharge. It's just the inverse. How much the energy or the discharge you have done, that becomes your depth of discharge. It is as simple as that. Now the next one is the rated capacity versus usable capacity. Till now we have seen that you have a voltage window and you cut off the voltage, your capacity has been dropped, etc., etc. Why do we need to cut the voltage windows? We can use the whole amount of voltage window. These are some questions by now you might have understood. You might have been cleared in an aspect, but you might not also been clear in some aspect. But this slide would help you in understanding. So the whole capacities of a cell can be treated in two ways: rated capacity and usable capacity. Rated capacity is a capacity which the cell is designated of. So for example, there is a cell of 100 Ah. That becomes the rated capacity. But that is some capacity which the manufacturer has manufactured it for. So the cell will be able to give 100 Ah when it is operated at its full voltage. But usable capacity is something which is controlled by the OEM who makes a battery pack, or it is controlled by the BMS or an engineer who is working on that cell, saying that I am going to limit the voltage windows, and because of that the capacity is going to fall, but still I am fine with it, which means the usable capacity is going to be less than that of a rated capacity. That is mainly because of the voltage cutoffs which we are going to do. So that is a reason why we have a usable capacity lesser than rated capacity. Now how and why is that happening? Now here we have a small image of that where we have lower line and upper line, which is the battery capacity, and when we fully charge it, there are certain stresses. When we are fully charged, there are going to be charge stresses, and then when we fully discharge it, we are going to have discharge stresses over here. So when we fully charge it, if we limit it to this percent, 80% of charge, and we limit it to 80% of discharge, we are going to avoid the charge and the discharge stress, and we will always be in the low stress zone. So this is the reason why most of the OEM manufacturers avoid touching the higher and the lowest limits always, and because of that the result is we would be losing the capacity. But that's fine when we are not allowing the cell to see the charge and the discharge stresses, which means the cell is operating at a comfort zone, which means we are going to have higher life cycles. So which means we'll need to slightly choose a cell which is having higher capacity, and then we are still fine with it. We will be having all the life cycles that we need. We will be achieving all the life cycles that we need to. So this is how we need to trade off between a rated capacity and the usable capacity. And how is it done? And it is done by programming the BMS by controlling the voltage cutoff. So next slide is like the BMS need and its functionality. So what is the BMS? BMS is called the battery management system, and it is the most important or the main control authority of the battery pack, which is responsible for safe monitoring and the safe functioning of the battery pack. So the major functionalities of this battery pack are like cell monitoring or cell balancing, which is one of the major tasks of BMS, where it monitors to keep all the cell voltages uniform through our operation of the battery pack while charging. So then we discussed on voltage cutoff limits during charging and discharging. Also, we have other safety features for the battery pack, which are temperature protection. That is, it will not allow the battery pack to operate above certain temperature limit. So and how is it done? This is all done through the BMS. This is all done through programming the BMS with the right values which are needed to give all these protections. And then BMS, that being sole communication authority with the BMS, and with the VCU, and it transfers all the parameters like SOC, SOH, all the error indications, or it could also transfer the data like battery pack temperature, operating temperature, whether it is safe or not, etc. So BMS communicates everything with the VCU, and then the VCU takes the appropriate decision what to do and what not to do. And then just not that, BMS also has certain protection features, like BMS also protects overcurrent C rates, like which means when the cell is delivering certain high C rates other than required, then that means the cell is misbehaving, and that kind of C rates are monitored. The BMS cuts off there itself. And also if the vehicle is demanding more power, which the battery pack is not designed, or which the electrical architecture is not designed for, the BMS immediately says this is not within my limit and I would not be able to deliver such kind of currents, and it terminates that command immediately. Such kind of precautions or protections is done by the BMS, which will also safeguard all the electronic components, electrical wiring harness in the battery pack, along with the cells, the incoming current and also the outgoing current. So this is all monitored by the BMS, which means the BMS becomes the vital component of the whole battery pack, which has to be programmed correctly, so that all these precautions and safety are considered while the BMS functionality. So now one of the major functionality of the BMS, that is cell balancing. So let us discuss about cell balancing. So why do we need a cell balancing? Like, we have heard about cell balancing a lot, but why do we need something like this? Because there are n number of lithium ion cells in a module or in a battery pack, and in a battery pack each cell can behave in its own way. Very difficult to bring all identical cells together, and even if we bring that, even though the behavior of each cell is going to be difficult, and hence when the cells are put to charge, what happens is one of the cell in a module can be charged quickly, whereas the cell which is right next to it will be charged slowly. That is what we see in the image over here. So one cell has reached its normal operating voltage range, another cell has reached more, another cell has reached little above, one cell is still less. So with such kind of voltage differences, when we put the cell for charging, if this happens, what happens is, until the other cells are being charged, the cell which has already been charged gets charged even more. It gets a current more and more and more and more, and which will allow that cell to deteriorate faster than the other slow cell which is getting still charged. It's not the fault of the cell which is charged fully. It's not even the fault of cell which is slowly charging. It is just that the cell which is overcharged, it's more healthier, but that has a toll on the cell which is slowly charged, because it is not charged, and that stabilized voltage will never be reached. So this could cause deterioration of a cell altogether. So that is the reason cell balancing is very important. So what cell balancing does is, the BMS, while doing a cell balancing, when it is put to charge, it will set a voltage level, say, or in the first image, where we see all the cells are at the same voltage window, which means all at the same level. Now, how is that achieved? Is, for example, we have cell 5, let us take cell 4. We have cell 4, it has reached its state 3.88 or near to 3.88, it is the first one to reach. Whereas the cell 7 is taking time. When it reaches 3.88, the cell 4 is not allowed to charge above this limit. So what happens is it stays over there, and the extra current or power coming to it either is dissipated as heat or it is transferred to the other cells, so that the other cells are charged quickly until cell 7 reaches its threshold normal operating temperature value, normal operating voltage value. So that's how it manages and says all the cell to remain at the same voltage level until there is 1 or 2 or 3 cells which it has reached its point, but it will not allow those cells to be charged more further, so that the voltage is still remaining constant over there. So that is what the cell balancing does. It doesn't allow the cell which is charged first to overcharge. It will still be there, it will still receive the charge, but either it can dissipate the charge as heat or it can transfer its charge to the other cells, so that the other cells can be quickly charged. So this is how the cell balancing works, and it is the most important part of the BMS to function, the cell balance. So there are two types of cell balancing. One is active cell balancing and passive cell balancing.
So this cell balancing, as I have discussed in the previous slides, as I said, that when it is an active balancing, the cell which is charged first
will send its charge to the another cells which are not yet charged. By doing this, one, the time for charging is reduced, because so other cells need not wait for the charger to send the power. The power which is coming from the overcharged cells is also coming to that cell. In that way, a lot of time is saved. But there is a huge electronic circuitry involved in doing that, and this active balancing consumes a lot of energy, and it consumes almost 3 to 4 times of what a passive balancing BMS would do. So active balancing is actually more complex, but it is very effective and it is very costly solution. So that is what an active balancing would do. So that is what it happens. Like for example, if we have 10 cells and 10 cells, one of it is fully charged and other cells are not fully charged, without any balancing it would run into a thermal runaway state. But by doing this active balancing, the extra amount of energy which it is being received is being transferred. But whereas in passive balancing, what happens is we have the same nature over here. But in passive balancing, instead of transferring the charge to the other cells, it dissipates the whole charge as heat. So which means that is not utilized in any form, but it also doesn't allow the voltage to build up by charging. So that is one advantage of having a passive balancing. At the same time, the circuitry of this passive balancing is quite simple, and it is the most widely used balancing technique across, though it is very economical when compared to active balancing, and also the power consumption by active balancing is moderately less when compared to active balancing. So the next slide, now we will discuss on the voltage cutoff limits through BMS. What happens when we apply the voltage cutoff limits through BMS? So usually BMS is nothing but an electronic board which we need to program the voltage limits according to the user's needs. So this can be done as and when required. It is all dependent on us. So, what are the voltage cutoff limits for the BMS? Let us just understand as per the chemistry again. What is this? For a typical LFP, lithium iron phosphate cell, we can see a maximum voltage is to be 3.6 volts, and the minimum voltage when it is discharged is 2.5 volts, and the nominal voltage is like 3.2 volts. And as per the manufacturers, we can expect a little bit of variation in this voltage level. And when it's an NMC cell, we have a maximum voltage of 4.2 volts and a minimum voltage of 3 volts and a nominal voltage of 3.65 volts. Hence, there are the chemistry standard, like these are chemistry standard voltage values which cannot much vary. Therefore, this voltage limits, as we understand, like these are the lower and higher voltage bands for a specific LFP and NMC chemistry, which have higher stresses at those ends of the voltage, and therefore when we chop off this end stress limits, we can reduce the stress and improve the cell life. So that is the reason where we always have to understand what are the voltage cutoff limits and chop off there. And by doing that, what do we get? By doing limits, what do we get? Now let us understand that with a pictorial representation. How do we get a capacity fade due to DOD limit? Now we have a cell which is having a voltage, we have assumed an NMC cell which is having a minimum voltage of 2.5, and it has a rated capacity of 3.25 Ah, and it has a maximum voltage of 4 volts. Now we have assumed a voltage cutoff of 2.8 volts. That means we have programmed the BMS to have a minimum voltage cutoff at 2.8 volts, and then which makes the usable capacity to 3.3 Ah only.